In this chapter, we're going to focus on the other two operations, multiplication and division. So I want to talk about multiplication first. And again, we want to say what multiplication is. And we want to do that in terms of things we've already defined and things we've already studied. And so there's two ways of looking at it. Both ways are equally as valid. So we can define multiplication as either, well, if we have two whole numbers a and b, then we can define a times b as, well, as a times b added to itself. So you add b to itself a times. So that's one way of looking at multiplication. Let's just do a quick example here. Maybe something like, let's do 3 times 4. Well, that's 3 times 4 added to itself, which is, of course, 12. Another way of looking at multiplication, well, we could go straight from sets, too. And if you remember from before, we have this idea of the Cartesian product of sets. And if you have the Cartesian product, remember, that's everything of the form AB with ordered pairs, such that your first element is in your first set, and your second element is in your second set. And if you go back to chapter 2 and look at that video, you could see how it relates directly to multiplication. So the size, remember this n here means the cardinality, the number of elements. The number of elements in A cross B is just A times B, which is great. So there are two models that two definitions that we could use to define multiplication. Either one is totally acceptable. There are some other models. Again, I'm just going to talk about one, but it's a good idea to read in chapter 3.1, the section on models for multiplication. That will be important. But one that's important, I think, for our purposes is this array model. So we can view a multiplication problem as a rectangle area thing. So if we have 3 times 4, well, we can look at a rectangle that has 3 units horizontally and 4 units vertically. Well, how many units squared does it have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Of course, it has 12. And that's going to be important to us later when we talk about some nice properties of multiplication. Just like with properties of addition, multiplication has some nice properties as well. So let's go over them. In fact, most of them are the same with addition, and they're the properties that you come to expect when it comes to multiplication. So to start things off, we're just going to pick 3 whole numbers. I'm going to call them A, B, and C. They could be any old whole numbers you like. So the first property is closure. Remember, closure says that if you have 2 numbers coming from a set, that when you apply the operation, in this case multiplication, to those numbers A and B in this case, here's A and B, and we're applying the operation multiplication, you remain in that set. You don't go outside that set. So that is closure. Of course, you stay in your set when you multiply. Commutativity, remember that word commute, which means to move around. That says that I can move around A times B to be B times A. Order doesn't matter. Associativity, see that word associate inside, which means grouping or buddies. All numbers are equal buddies. So it doesn't matter how I group them. I can do A times B, then times C, or I can do A times the product of B and C. It doesn't matter the order that I figure them out. And again, a lot of people will just write A times B times C without any brackets there because multiplication is indeed associative. Now we have this identity element in the whole numbers. Remember, identity in math means it does nothing. And with multiplication, what number does nothing when you multiply? Of course, it's 1. There is a 1 inside the natural numbers, such that if I multiply any number I like by 1, I get A. So that's the multiplicative identity. 0 plays an important role. Of course, if you multiply any number by 0, you get 0. And there is a 0, of course, in the whole numbers here. And then the final property I want to talk about, and in some sense this one is the most important, because it tells you how multiplication and addition play together. So let me tell you the rule, and then I can explain how it works. So if I have A times the sum of two numbers B and C, well, what I can do is I can distribute that A to each part of the sum. And a lot of people think of it like with arrows. They'll draw this when they distribute. So it's A times B plus A times C. And the best way to think about it, let me do a little example here. So I'm going to do a specific example of this general statement. This works for any three whole numbers you like. But the specific example I'm going to do, I'm going to say in this case A is 5, B and C are 6 and 2. So we're going to use the array model to think about this. And you can imagine if I had a rectangle, you could think of it like a chocolate bar. If it's 8 squares by 5 squares or 8 units by 5 units, what's the area of this rectangle, or how many blocks are in this chocolate bar? Well, of course, it's 8 times 5, which is 40. 5 times 8. And I'm just going to write 8 as 6 plus 2. Why not? That's the same thing. That's 40. Of course it is. But what I can do is I can break up this chocolate bar and figure out the area of both sections I break it up into. Obviously, the amount of rectangle I have stays the same. It's just in two different pieces. I'm not getting rid of or adding any area to what I have. I'm just splitting it up into two separate chunks. I could figure out the chunk of each and add them together. So that's what's going on here. If I broke it up here with 6 and 2, I could figure out the area of the top chunk. Well, that's going to be 5 times 2. And the area of the bottom chunk is 5 times 6. And now if I add these areas together, of course, I get the area of the entire rectangle. And that's what the distributive property is doing. That's all you're doing. So when you split it up into two separate sums like this, you're just kind of breaking up your rectangle into 2 bits and figuring out, or I should say 2 or more bits, in this case 2 bits, and you're figuring out the multiplication for each of them and then just adding it together. A quick note about distributivity. So we showed it kind of just for one number multiplied by a bracket that had 2 things in it. But this holds in general for everything. In fact, let me kind of show you just why this holds in general for everything. I'll just do a little thing here. So 7 plus 5 is the same, of course, as 12. So I could write this as 12 times 3 plus 4, and then do 12 times 3, use distributivity, plus 12 times 4, and then say, hey, look, 12 is 7 plus 5. So we do 7 plus 5 times 3 plus 7 plus 5 times 4, and then do distributivity again. I won't finish that because you just get the line up here. You just get this stuff. But you could just use distributivity the way we defined it twice, but the way everybody kind of thinks of it is as follows. So you take every term in your first bracket, and you multiply it by every term in your second bracket, and then you add them all up. So here we have 7 times 3, then 7 times 4, then 5 times 3, then 5 times 4. There they are there. And a lot of people refer to this as FOIL. First, outside, inside, last. But I don't like that FOIL analogy because it's really obscuring a kind of an easy idea that can be applied to however many terms you have in your brackets here. But again, the idea is the same. We're just breaking up our rectangle into different size blocks. So here we have a 12 by 7 rectangle, and I'm going to break this vertical dimension 12 into 2 pieces, a 7 and a 5, just by putting a cut there. And then I'm going to break the horizontal dimension 7 into 2 pieces by drawing a vertical line here. Here's a piece of 3 and a piece of 4. And again, all I'm doing, I have these small rectangles here. This small rectangle here is 7 by 3. 7 by 3. 7 by 3. And of course, the area of that is 7 times 3, which is 21. So that's this 7 times 3. Here we have 7 times 4. 7 times 4 is 28. And then we can look at the bottom ones. 5 times 3 is 15, and 5 times 4 is 20. So you can check if you like. This adds up to exactly what you expect. 7 12s are 84. But if we do it in pieces like this, again, by looking at the diagram, you should see that we are going to get exactly what we expect. There's no adding or subtracting of area. We're just breaking it up. So this is 21 plus 28 plus 15 plus 20. And you can check by a little hand calculation that gives you exactly what you expect, 84. So, looking at this idea, here are 2 examples I want you guys to try and draw out. I know you can just FOIL these, no problem, but draw a little bit of a diagram to convince you that this idea of distributivity does indeed work. And so you can see what's going on with each term in your distribution there. So this is a good model of distributivity, is drawing this rectangle and breaking it up. So do that for both of these. This one is kind of the same. It has an a in it. All of these variables here have an a in the first one and an x, y, and a z. All of those you could think of as whatever whole numbers you like. So these are just some arbitrary whole numbers. And then once you draw the diagram, just calculate the calculate and simplify the expression here. So you'd expand this out using distributivity, just like we did above, and simplify, combining like terms, etc. And then for the second one, same idea, but now we have 3 terms in each of the brackets. So we're going to break up our rectangle into 3 by 3, which is 9 pieces rather than 4 pieces here. So we're going to break up each dimension into 3 separate pieces. So give that a go and see if you get the correct answer, and make sure that it makes sense to you. All right. So let's look at question 1 first. I didn't quite finish off question 2. I'll finish it off while we speak. But let's do question 1 right now. So if we look at the diagram, just like before, we broke this up into a plus 7 and then 2a plus 1. And we're figuring out the area of each of these 4 subrectangles. And notice that I kind of did the the first bracket horizontally rather than vertically, like up here. It doesn't matter if you have it as the horizontal or vertical dimension. Same idea happens. Okay, so 2a times a is 2a squared. 2a times 7 is 14a. A times 1 is a, and 1 times 7 is 7. And you can see this from distributivity. Well, let's multiply the a by both terms. So a times 2a is 2a squared. A times 1 is a, so that's these guys here. So that's the a bit of the horizontal dimension here. And then the 7-bit, 7 times 2a is 14a, 7 times 1 is 7. That's the 7-bit of my horizontal dimension. I have them underlined with the appropriate colors. And then, of course, we just combine our like terms. So I notice that I have an a and a 14a. Adding them together, I get 15a. So the final answer for this one is 2a squared plus 15a plus 7. For the second one, well, again, all we're doing, rather than breaking it into 2 pieces in each dimension, we're breaking it into 9 pieces in each dimension. So 3 plus x plus y, 2 plus x plus 2z. And then we just figure out the product for each of these 9 subrectangles. So 2 times 3 is, of course, 6. And we do that for all of these. Another one, say x times 2z is 2xz. Notice I just kind of write the variables here in alphabetical order just to have some sort of standard so it's a little bit easier to see what's going on. Remember, multiplication is commutative, so I can write these in whatever order I like. So we have x times 2 times z is 2xz, 2 times x times z. So there we go. And so we can write that down using distributivity. Again, all we're doing here, when we do kind of the first term times each term in the second bracket, so this 3 times 2 times x times 2z, that is, I'll highlight it in red here, that is this bit here. So that's the 6 and the 3x and the 6z. 3 times 2, 3 times x, 3 times 2z. And then we do the x times every term there. We'll do that in blue, I guess. So of course we get 2x, x squared, and 2xz. So that's going to be, let me write it with some arrows. So x times 2, x times x, x times 2z. And that is, of course, these 3 guys. And then finally in green, well, we have y times each of the 3 terms in brackets. So that is these 3 guys. I guess I'll go up as well. And that is, of course, 2y, xy, and 2yz. Now the last thing we have to do is combine our like terms. I'll just move everything up to give myself a little more room. So let's look. We only have one constant, so we'll keep that. That's the 6. Let's look. Do we have any other x terms? And whenever I write something down, I like to just put a little dashed line through it just to make sure that I cover all of my terms. So I have a 6. Let's look at my terms that have an x. So I have a 3x. Do I have any other terms with an x? Well, I have this 2x. And I keep looking, and that is it. So 3x plus 2x, well, we must have 5x's then. 3x's plus 2x's is 5x's. Let's do the z's. Well, in fact, we'll find with each of the other terms, there's going to be no repeats. So I'll write down plus 6z plus x squared plus 2xz plus 2y, I'll just write these down, plus xy plus 2yz. So in this case, there was only 2 terms that we could combine, 2 like terms, this 3x and this 2x. All of the other terms don't have the same variables. So that is all we can do. But anyway, that's all that's going on with distributivity.